Hello everyone, welcome to another session of MathLab Talk. Today's talk will be given by Aditya Prabhu from third year, BMath third year, and the topic is free groups. We'll be talking about subgroups of free groups and how that relates to folding of certain graphs, and we'll explain what he means by folding. It'll be an interesting topic. So, over to you.
Thank you, Saraswata. Thanks to you guys for being here. Let's start. I hope everyone can hear me. Fine. Okay. Good. So I'm going to assume that you guys are familiar with what free groups are because I think you guys have done it in your course with Suri, and some other people have also done it. So let's just assume what free groups are. But I'll give you an overview of what how we define them. So we start with a set S. Okay. Okay. We say that elements of S are letters. Then we look at the set S union S inverse. S inverse is the set of formal inverses of all these letters. Okay. Now we take letters from this set. Okay. And we form finite length strings with them, which are called words. Okay. So while I define this, I'll just give you an example on the side, which is F2, the free group on two letters. Okay. So we start with the set AB, close it with their inverses A inverse, B inverse. Okay. And now we take finite length words on these letters, which can look like A squared. Well, when I say squared, it's just A, and when I say inverse, it's just this inverse letter there. And then I could have something like A to the minus 3, whatever. I could have any word like this. Okay. We reduce these words according to the relations of the form U inverse equals identity. Okay. So these are called trivial relations. So an element times its inverse is identity. This is what every group must have. So that's why we call it the trivial relation, because every group has it. Okay. And we form all sorts of words, and then we see if there is an occurrence of a letter and its inverse one after the other, then we replace it with the empty word, and that's what we are doing. That's called reduction of a word. Okay. So you reduce all words formed from these letters and you get reduced words, obviously. And now my claim is that the set of all reduced words over the set S union S inverse forms a group with a particular operation, and the operation is string concatenation followed by reduction. Okay. So what that means is, if I had two words to begin with, so I could take some word of this form a cubed a to the minus 2, but this is not a reduced word, so I could reduce it, and this is the reduced word corresponding to this one, right? Or I could have some other word which could look like a inverse b inverse a squared, something like this. Okay. And what is the multiplication of these two words? You just concatenate the two strings, so write them one after the other. Okay. And then perform the process of reduction on this word. Okay. So this a inverse is 1, so it's just b inverse a squared. Okay. So I'm claiming that the set of all reduced words with the operation of concatenation followed by reduction forms a group, and that's called the free group on the set S. So this was the example of free group on two letters. Hope you guys understand. Sorry, what does that mean? What do you mean exactly? Yeah, cyclically consecutive doesn't matter. So you are saying if there's an A inverse at the start and there are some things in the middle and A at the end, then we cancel them off. That's not true. Yeah, only linearly. So I claim that if position I and position I plus 1 have some U and then some U inverse, then I reduce them into the identity. Right? Okay. Any more questions? None. Okay, I'll just move these up. Right. Fine. Some observations there. In free groups, you can't have elements of finite order. Okay. Why is that? Because so why is this group called free? Because I'm reducing words only with this relation. Okay, this is the only relation I care about. This is the relation which is there in every group. I only care about this one. Groups can have special relations like abelianity. Not all groups have abelianity, but abelianity is a relation. Or groups can have elements of finite order, or they could have some two non-trivial elements multiplying to give you the identity. There are so many things, but I'm saying that none of those things happen in this group. So this group has no restrictions, hence it's free. Okay. Yeah, so a free group can't have fs, so free group on the set S, that's how it's denoted, can't have finite order elements it can't have abelianity unless the size of S is 1. It can't have any other trivial relations also, but these are some of the simple ones. So if you're just looking at a group and you find some element which has finite order, that's not a free group. If you're looking at a group and it has abelianity, unless it's Z, it's not free. Okay. It's not ready. Use that. Significantly harder. Okay. Fine. So subgroups of groups come up everywhere, right? So we want to study what subgroups look like. So now there is this result that we did in rings and modules last year for B3, that subgroups of free abelian groups are free abelian of a lower rank, right? This is something we did. So there is so if you don't know what that means, it's okay. This was just to give some motivation. But there is this thing called the Nielsen-Schreier theorem, which gives something similar for free groups. So the Nielsen-Schreier theorem says that if G is free and H is a subgroup of G, then H is free. Okay. So now this is quite a nice result. You may not see this in the first glance, but this is a nice result. So let's see what I'm trying to say. Okay. Let's take, so throughout this talk we'll be talking about F2 mainly. Okay. The free group on two letters. The two letters will be considered to be A and B usually. So right, I'm looking at F2. I could look at the subgroup generated by the letter A, right? So what sorts of things will this have? You have A, so you definitely have to have A inverse. You will have A square. You have A to the minus 2. You have the empty word always, because in every subgroup you have to have that, and then you'll get all the powers. You'll get all the powers there. So this is isomorphic to Z, right? And Z is the free group on one letter. So I've just verified this theorem for this particular subgroup. The subgroup generated by a certain word is free. I could also look at the subgroup generated by these two words, A and AB. Okay. So what would this subgroup be? So it will definitely contain all of these powers. It will also contain all the powers of this. It will contain all the products and then inverses and then inverse and then some power product and all these different things, right? So what is the isomorphic to? So it turns out this is isomorphic to the group generated by A and B itself. And you can see that because A is already there in this, right? And you can just, since A is there, A inverse is also there, right? And then A inverse is there and AB is there. So you can just multiply A inverse and AB and you get B. So now A and B are both there. So it generates the full group, right? And this is again, so the full group is, okay, sorry, this is the group generated by A and B, which is isomorphic for the free group on two letters. So this is also free. Now, so these were easy to verify, but please ask me any questions in the middle. Don't hesitate to interrupt. Okay. So I looked at those two subgroups, right? What if I had some more complicated subgroup? What if I took three random words? I just make a b a inverse, b squared a to the 37 b inverse, and then a b squared. These three words. By the Nielsen-Schreier theorem, I know that the subgroup generated by these three words is free. It may not be free on these three words themselves. Okay, so what that means is, well, these three words in themselves, they may have some relation, but there will be some generating set for which I can prove that this group is free. Okay, that's what the Nielsen-Schreier theorem is saying. But now I don't know anything about this group, right? If you try to figure out what this subgroup looks like, it won't be that easy, because you'll have to multiply, and then you may not even, I don't even know at this point if A belongs to this group. I don't even know that, right? Let's call this H, right? I don't even know if A belongs to H. I don't know what the rank of this free group is. So, okay, I had written, yes, subgroups of free abelian groups are free abelian of a lower rank. That is not the, so this part of a lower rank isn't true in free groups. Okay, you can have subgroups of F2 which are isomorphic to Fn, like the free group on countably many letters. So it's, this sits inside F2. That's what I'm saying. F3 also sits inside F2. F4 also sits inside F2, and it's all bizarre because we're in the non-abelian setup, right? So no, it doesn't. Okay, fine. So free groups, they, you just take words and you form all sorts of words and you reduce them according to u inverse equals 1, right? If you additionally impose the restriction of abelianity, you get a free abelian group. Why doesn't it make sense? Nahi, z square is also free abelian, right? Now, okay, so this is misleading. So when I say free abelian group, I'm not saying this group is free. Yeah, it's kind of misleading. Yeah, you might think that, oh, this is a abelian group which is also free, but that's not what I'm saying. I'm saying it's a free group with the additional restriction of abelianity. It's so close to free that I'm calling it free. No, it's not. It has the relation of abelianity. That's why it's not free. But that's what we call these groups. We call them free abelian. They're not really free. Yes, that's a. Huh? Yes, free Z modules, exactly. Yeah, yeah, they're called free abelian, but they're not free. Exactly, yeah, that's it. You have the free group on n letters, and then you go mod the commutator of all pairs of letters. You make every single generator commute with every other generator. So you have added the abelianity relation. Huh? If you add abelianity to? No, if I increase the number of generators, then it will be z square and z cube and so on. Yeah. Yeah, but the thing is, the Nielsen-Schreier theorem says that you can have subgroups. The subgroups of free groups are always free, but they may have any sorts of ranks. Okay, so I took these three words, right? This group could be isomorphic to the free group on 3 letters. It could be isomorphic, so question mark. It could be isomorphic to the free group on 2 letters. It could also be isomorphic to the free group on 1 letter. It could be trivial. You don't know. Okay, so how do we figure this out? And that's the question we want to answer. So there are certain number of questions that we want answers to, and I'll write them all, and then we'll see how we get an answer to these questions. So the surprising thing is, I'll write these questions and these will seem like they are difficult questions to answer because we don't know how to think about this subgroup yet. But then I'll introduce one model, and then there is a very simple thing called folding, and you will be able to see that all these questions are very simple answers. So the first question is, what is the rank of H? Right? Rank is how many generators is H free on. Okay. So for example, the rank of F2 is 2 and the rank of F3 is 3 and so whatever. Okay. What is the rank of H? What are the generators? Right. This is a question because let's take a different example. Let's say I had taken okay, fine, maybe I take a squared a cubed, right? I take these three letters and I see the subgroup generated by them. This will be just the subgroup generated by A, right? And this is free. Now this is free on this one letter, so I know that the rank of this subgroup is in fact 1. Okay, rank is 1, and I know that the generator is A. So that's my question. If I give you some arbitrary group, and I could have as many words as I want, as long as there are finitely many. So I could have W1, W2 up to Wn, and given this subgroup, how many? What's the rank of it? What are its generators? Can I find these generators in terms of the previous generators? So if I write that this is A, can I write A as one of these previous things? Now here it's obvious, but can I do it in general? The second question is yes. Okay. Right. Is W in H? Now what is W? W is some word. If you just write down some word of F2 in this group, for example, can I ask the question, is AB to the 45 inside H or not? This is my question. How will you find this? This is insanely difficult to do, but this method will give you a very nice way to do it, and this is my favorite. But let's see what this works out to be. Is W in H? So this is called the membership problem. Okay, membership. Then the third problem is, what is the index? What is the index of H in F2? Is H normal? So these are the 4 questions I have, and I will not erase these hopefully till the end. And now I'll give you the answers to these questions, and we'll see how easy they are. Okay, so let's start with that one first. Okay, yeah, fine. So we will be working with some graphs. Okay, you know that a graph is some vertices and edges all a graph. Okay, but here the graph will be directed, labeled, looped, multiple edges, everything will be there. Okay, so it won't be simple by any means. Right, so you have a graph. I'm going to describe this thing called a fold. Okay, so if you look at a vertex V in the vertex set, okay, and there are 2 edges coming out of it, both with the same orientation. So for both, this vertex V is the beginning, the initial point, okay, and both of these edges have the same label. Let's say the label is A or something, okay, and there is some more edges, we don't care about those. Okay, after a fold, what I'm going to do is I'm going to identify these 2 edges together, and consequently their vertices also get identified together. So 2 edges turn into 1, and these 2 vertices also turn into 1. So I'm going to effectively get just this one A edge, and whatever was there just stays as it is. So these 3 were here and these 2 were here. Does this make sense? Simple enough, right? This is what a fold is. Now I could describe this for more complicated situations also. So if I had just one vertex and okay, so maybe I had 2 vertices and then 2 edges coming out. So multiple edges between these 2 vertices with the same label and the same orientation. So same orientation, by that what I mean is I couldn't have this. Okay, this sort of a thing can't be folded. They both must have the same initial vertex. Okay, so this sort of a thing is there. I can fold this and get just these 2 vertices and one edge between. Make sense? Folding is just folding. That's what I'm doing. Okay. Okay. So how do I define orientation for? Inward, like this. Yeah. So that can't be folded because for each edge you will have, so the edge will be an ordered pair, right? Like v1 comma v2. So 2 edges v1 comma v2 and v3 comma v4 can be folded if and only if v1 is v3. This should be equal, their initial vertex or their final vertex, either one of the two, and their label should be the same. So whatever labels they are, they should be the same. Then I can fold them and get this. is if there's an edge between the here this that does not, no. Yeah, it'll become a loop. So if there is an edge here, what you're doing is you're still identifying these two, but then you're not doing anything with this extra edge, right? So it kind of becomes a loop now because its initial and the final point are identified in the folded graph. Make sense? Cool. Okay. So these were two types of folds. Another type of fold could be if I had a loop at one point and then an outgoing edge. Okay, I can fold this outgoing edge around this loop. Does that make sense? I'm taking this endpoint and I'm folding it around the loop. Okay, makes sense, right? Because this condition is still satisfied. The initial vertex is the same, except for the loop. It's the initial and the final both are the same, but we don't care about that. So we can identify these two, whether labels have to be the same always. Okay, and get just one loop. Make sense? Yeah. Okay. And the last case is if you have two loops with the same labels, you can again fold it, but now I can't demonstrate, or you can just think of maybe folding it like this. The paper is folded on top of the other, but the same thing is there. The condition formally would be if you have an initial vertex and there are two edges coming out of it and they have the same label, then you identify the two edges together and effectively that's what it is. So these two loops will go to just one loop. Okay, so these are the operations we are going to work with. It's called a fold. And right, now we have what we need. Okay, I need to write it down. Okay, let's try to write it down. Just go to erase. Let's erase it here. Okay. So you start with two graphs. Okay, fine. So everything is finite in this talk. We don't have these things for infinite graphs. You start with two graphs, gamma and delta, and this is a graph map. Graph map meaning that edges go to edges, vertices go to vertices, and vertices which are adjacent here have to be adjacent there also. Okay. So if gamma to delta is a graph map, let's what can this be? P. Okay. Gamma to delta is a graph map. Then yes. Okay. Take a V belong to the vertex set of gamma. Okay. Now if E1, E2 belong to the edge set of gamma, and okay, so I'm writing E1 and E2. I'm writing edges as pairs of this thing. Okay, like V1, V2, and then V3, V4. Okay, and either V1 is equal to, so this is E1, this is E2. Okay, either V1 is equal to V3 or V2 is equal to V4, and under P, E1 and E2 map to the same thing. Okay, well, I don't really need to say that they need to map to the same. Sorry, huh? Yeah, they're directed graphs. They're all directed, labeled, loop. Everything can be there. Okay, but yeah, that's why I wrote ordered pairs. Yes, it should be. Yeah, so it preserves all the structure that we have on these graphs. So the directions have to be, sorry, the orientations have to be preserved, and the labels have to go to the same labels, and yeah, the adjacency must be preserved because it's a graph. Okay, and this is the case. Then, okay, well, E1 and E2 are the same. Okay, so then gamma dash or gamma folded, that can be defined as a graph with the vertex set of gamma except for the end vertex. So now this will be tedious to write down because if these two are equal, then these two are identified, and then if these two are equal, then that two are identified. But you get the idea, right? Huh? Yeah, one of the vertices are equal, and you remove the one which is well, you don't remove the one which is not equal. You identify them together. Uh, I'm not sure how to write this down formally. I'm not sure how to write down the vertex set and the edge set, but you're removing one of the vertices. You're removing that edge effectively, and the other edges remaining, and the vertices are labeled again. I'm quotienting by that edge, yeah, right. But okay, right. So I identified V3 with V4. Okay, yeah, V2 and V4, sure. Okay, makes sense. Yeah, that makes sense. Right, gamma mod tilde, right, and then the edge set is defined by this vertex set. Okay, right. Okay, so yeah, this is here. So this is what. So any other questions? It's fine. Okay, good. Then, hmm. So we'll do this example. Okay. So I'm not telling you how any of this is going to work right now, but we will do this one example and it will be clear after a while. Okay. Right. So the example is this. H is AB, AB inverse, AB squared, BAB, and BA cubed, B inverse. AB, AB inverse, AB squared, BAB, and BA cubed, B inverse. Fine. Okay. Yeah. So this is what H is, and we want to find out the answers to those questions for H. Okay. So how do we do that? We'll start. Okay. So we'll start with this graph. Okay. So keep a vertex in the middle. Start with this vertex. Draw these petals. Okay. Each petal is going to be for one word, and now I'll tell you what to do on these petals. So there are these four things, right? So drop three vertices here. Okay. I want to make these petals such that, so this is my base point. Okay. In this topological space, this is my base point. So graphs here are topological spaces. So I can talk about half of this edge and then one third of the edge and so on, but it doesn't really matter. Okay, so this is my base point. I want to make the petals such that when I read what the generators are in this order, in whatever order, they should tell me that those are these words. So for example, uh, right, okay. So this would be A, B, A, B inverse. Does this make sense? So what I've done is I've labeled the edges such that if I start reading from this side, I will get A, B, A, and then there is a B, but the orientation is reversed. So it will be B inverse. Okay. So effectively, I'm saying that edges which come in with a certain orientation, they're labeled as the inverse of that letter. Okay. So now I've labeled this particular word here. Then it's AB squared. So this is A, B, B. Makes sense? Yeah. Then okay, is this visible? Right. Then BAB, there is a B going down. I'll change this diagram a little bit later, but yeah, there's a B going down, a B going here, B going up. Makes sense? BAB, right? And then there is, okay, well, this one is going to be BAA. Okay, so there is a B, there is a, there is a, there is a, and then there is a B inverse. Okay, so makes sense. We start with this graph. Okay, we are going to fold this graph. So what folding means is I'm going to look at every vertex. I'm going to see, are there two edges? I'm going to ask myself this question: are there two edges with the same orientation and the same label coming out of that vertex? If yes, fold them together. If not, just continue to the next vertex. Okay, I'm going to perform folding on this graph until it can't be folded any longer. Okay. The Cayley graph, it's Okay. I don't really understand how this is a Cayley graph, but maybe it is. I'm not sure. Uh, well, yes, yes. It is not the Cayley graph. Okay. Right. That is it. That's what. Yeah. It's not the Cayley graph, but okay, nice. Fine. But we are going to fold this thing and then we'll get something. We'll see what that is. I'm just seeing if I have to define anything before that. Do I need? Yes. Okay. Let's do this thing. Okay. So there is this theorem by Stallings. Okay. The theorem says that if gamma to delta is a map between finite graphs, then it factors as gamma equals gamma naught to gamma 1 to gamma 2, so on, so on, so on, up till gamma n to delta. Okay, where gamma to gamma I plus 1 is a fold and gamma n to delta is, so this IMM is an immersion. I'm not writing it because there's not enough space there. I'll just tell you what this theorem is saying now. I don't want to erase, so let's just, I don't want to erase any of this. Don't have enough words. It's fine. Let's erase these. I'll come back to these foldings again. I mean, I'll just recall them later, but it's fine. Do we have time? Oh, sure. 20 more minutes? It's fine. So this is a theorem. So do you guys get what I'm saying? There is a graph map. So in this case, what the map will be is our underlying space is, well, we want to look at F2, right? So we map this onto the wedge of two circles, okay, which is this, one with an A, one with a B. Okay. So what the map is any edge that is labeled that is labeled A goes to that A loop, and any edge that is labeled B goes to B loop. Okay. So that's the map, and yeah, this is a graph map. Okay, you can verify this is a graph map. And what this theorem by Stallings says is, if these two are finite graphs and I have a graph map between them, then it factors as folds. So what that means is I can fold gamma and I can keep folding gamma. Since it's a finite graph, the folding process has to end at some point. And this last graph that I get, gamma n, that will admit a map to delta, and that map will be an immersion. So what is an immersion? An immersion is a locally injective map. Okay, locally injective. So what does that mean? Is this map locally injective or not? So if we look at this vertex, we can see that there are two A edges going out, right? Both of these edges are going to this A edge. So it's not injective at this vertex, right? Because the pre-image of this is not defined here, right? So so I'm saying that a finite graph can be folded enough times so that at the end I will get an immersion, a locally injective map. So in particular, you should see that any map which can't be folded any longer. So if a map is an immersion, that means like two things are not going to the same thing. That means we didn't have two edges going out of a vertex with the same orientation and the same label. If they were, then they would have gone to the same thing and made it not injective. Right. So this immersion wala graph, that will be a non-foldable graph. Okay. Fine. So now we have what an immersion is, and okay, good. Yeah, fine. So now the algorithm that we have is this. Okay. The algorithm is You take given h, construct gamma of h. Gamma of h is the map, is the graph defined this way, so that the petals read off the words of that subgroup, right? So define gamma of h, then fold gamma of h as long as possible. So you are folding this as long as possible until you get delta h, okay? And from delta h to r2, so r2 is this wedge of two circles with two petals, right? I mean the rows with two petals, or the wedge of two circles, okay? So this map will be now an immersion, and delta h can't be folded any longer, right? uh, right, okay. So now all that we are going to do is we are going to fold it enough, and then we are going to focus on this graph delta h, and this will give us all the properties of whatever we need to find. So this now, okay, now let's just do this process for this graph, okay? So I'm going to draw it a little bit more nicely. Let's just okay, okay, fine. So this is the same graph as that. I've just labeled them differently so that the foldings are easier to see. So if you don't believe me, just look at this. This is a b inverse, right? Then this is a b squared. Then this is b a b, and this is b a b inverse, which is b a cube b inverse. Okay, so that's exactly the same as that. Now I'm going to show you what folding looks like. This is just one step at a time. What you can do is look at this vertex. Okay, this is our vertex. See that these two B edges have the same label and they have the same orientation, so I can fold them together, right? I can identify them together and I get this petal back, right? uh, this petal exactly as it is, and now this petal will start out here, and then there'll be a B edge going here, and then there is the rest of that petal from there, and it comes here. Okay, fine. So the upper petal is exactly as it was, that is just uh, a b a b inverse. Okay, then this petal is also exactly as it was, which is just sorry, it's just b, then b a a a, right? B a cube b inverse, and the last one, this one is just b here, a here. This is our b edge going in, which we just folded, right? Then an a here and a b here. Yes, that's it. Does this make sense? Fine. So what I've done is I've identified these two together. Everything else stays the same, and this is one fold. So this is our gamma one. Okay, and you could have folded anything else, but it turns out that at the end the delta h that you get will be the same. Okay, because all our properties depend on delta h. Right. Okay. So now notice this thing. Okay, so we can perform folds one by one or one at a time. They're all the same thing, right? So instead of drawing so many graphs, I'm just going to look at this. There is a b edge coming out. Again, there is a b edge coming out. There is a b edge coming out. There is a b edge coming out, right? 4 b edges. I'm going to fold at once. Okay, fine. From there, okay, how do I do this? Right, so there's going to be this vertex comes till here. There is a b edge going here. There is an a edge going here, right? there is this going here. So these are unchanged. So I'm not identifying anything from this part, right? This part is exactly as it was, so I'm just keeping it there. Now all these B edges, so this B edge and this B edge and this B edge and this B edge, they are all getting identified. So here A, B, and there is a again. Okay, this is this part. Okay, till here. After that, well, this is the folded B edge. Okay, all these four edges I got identified to this one edge now. And what's it doing? Well, it has, so these two got identified, right? So this entire part of 3a's here, that turns into a loop now. Not a loop, a cycle. Right? We have these 3a's here. Okay. Then these two got identified, and these two also were. So again, these two also got identified, right? So this point, which had a edge going to this point, also comes here. Okay, and the orientation is exactly the same. Okay. I think this should be our graph. It's coming in. Yes, this is our graph. Okay, after folding. Good. Now down. This is this. We'll go there later. Okay. Again, we can look at these vertices and okay. So just for the sake of it, let's keep track of the base point. Okay. This was our base point there, and that is this one here. Okay. It doesn't really matter, but I'm just going to say that's our base point. Now what can I fold? I can, maybe you guys can also tell me. Look at it, and if there's any edge you see that can be folded, maybe we'll do this ones. Sure. Yeah. So let's fold those. So we have these three here. A. A. These three are the ones here, right? Then the B edge goes here. Okay. Then there is an where does that go now? Okay, so there is an A edge coming from here, which is here. Then the other B edge should go and identify itself here, right? The vertex gets identified here. This is a B edge now. This is an A edge now. That makes sense. Yes. Okay. And this is now. Yeah. Makes sense. Okay. And there is a B edge going out here. Keep track of the orientations also, okay? Because if you miss one orientation, we're going to get the wrong graph. But this is fine as long as it is here. Okay. P, and then there is an AH going from here. Fine. That makes sense. I've folded these two together, and I've gotten this graph now. What else can be folded? The 4 edge. There is an A going out. There's a A going in at this vertex. You're saying. So we fold with this loop. That's what you're saying. Oh, you're saying these two and these two. Okay. Let's do that later. Uh, so right now this is a cycle, right? So let's keep the cycles at the end, and at the end we'll get a nice picture. Something else, maybe these two edges. Sure. Okay. So let's do the simple things first. But yeah. Okay. Now after folding that, you'll get the loop here, right? Huh? I know. Yeah, I get it, but still, it's okay. Just bear with me. There is an A edge going out here. Now these two got identified. So there is a B edge going out here, right? Now there is an A edge which comes there. Nope, the other way. Okay, and there is an edge which goes from the bottom to here. Make sense? It's fine. So we identified these two B edges now. What else can we do? Little late. Fine. uh, okay. What else? Oh, now I suppose I have to do that, huh? Yeah, I had to do that anyway. Okay, I thought it would be much simpler than this, but fine. We identified these two, and that's much messier now. These two together. Which two? Huh? Huh? Where is that? Here, correct? This B edge, na? This B edge. कहाँ पे? From which cycle to where? This is right now. Okay. Uh, yeah, I still can't fold anything over there. Yeah, I can't. Okay. So let's just go with the original suggestion and try to. Huh? I have folded. I have folded these two edges together. Yeah. Yeah. Okay. So now let's fold these two together. Okay. I'm just going to do it right here. Okay. I'm not going to change this graph. This A edge is now getting identified with this A edge. Okay. Again, these two are getting identified. Okay. That will give me just one edge, right? And now, rather than doing that, okay, I should just do this. This now. I have forgotten the orientation. There was an A there. There's an A going this way. Do you get this? So what I've done is I've identified this edge with this edge, right? So basically this vertex goes here. That's what this is shown. Now again, my god, this is, I should have drawn this in a much better way. But now this gets, yeah, these two are again incoming edges, right? So they get identified together. So I've basically taken this vertex and put it here, right? Does that make sense? Please be careful. Sorry for यहाँ पे एकदम कर रहा हूँ इस corner में. But yeah, so there is this. Yeah. So what I'm doing now is identifying these two edges. Okay, there is this A going in and there is this A going in. So when I identify them together, this vertex comes here. Okay, effectively turning this edge. This is an edge, right? Yeah, this is an edge. Kya. Yes, that is an edge. Yeah, okay. Effectively turning this into a loop here, right? And does that make sense? Yeah, it goes there. It turns this into a loop, and nothing else changes. Okay, so goes there, turns this into a loop A. Huh? Remove the. No, the top edge is still there because I had these three things, right? So this edge got identified with that one. So the edge is still there. You can't remove the edge, right? Like you see this. कौन सा point is which this point? No, it's not. It's not. See what's happening here is this edge, it's getting identified with this edge, right? So uska initial vertex will stay as it is, right? The common vertex is staying as it is. The end point is getting identified with this end point here, right? So it kind of goes there, right? Whatever. So this is fine. Do we agree with this? Okay, great. We're in agreement. Now what can we do? Well, okay. So now once we have a loop, everything gets easier because now no matter what orientation the edge is in, like if there's a A coming in or a A going out, you can always fold it, right? Now this edge can be folded with this edge can be folded with this, right? Both of them get folded. and effectively make these two things disappear, and there is only one loop here. Does that make sense? Fine. So this turns into, there is an A going here, there is a B going here, there is a B coming back here, there is a loop here, uh, and this B is coming here. Make sense? So now I've gotten this graph. What have I done? I have taken this edge, A edge, and identified with this loop. Okay, that effectively brought this point here, making this one into another loop. And I had shown before that two loops can just get clubbed together. I don't care about those, right? So now I have this graph. So again, okay, now good. Now we are at the last step. You see that these two B edges, right? This B edge is here and this B edge is here. They have the same orientation, same label. So I identify these two together. I fold them. So this point gets identified with this one, right? That gives me a loop A at this point, right? And then there is a B going here, B going here, right? There is a, make sense? What we have done is we have folded these two edges together. Okay, we've gotten this. And if someone knows Algebraic, then this is the covering space of the other one. Doesn't matter, but just a thing. A is here, so this is our base point. Okay, so now this is our delta H. Okay, so what we'll call delta H. This was the gamma n here. Okay, this is the unfoldable graph. So now we have an immersion which goes from delta H to R2, and you can do that. You can see at immersion is a locally injective map, right? So at this point, am I getting two edges that are going to the same edge? No. Am I getting two edges that are going to the same edge here? No. So it's an immersion. And okay, now I'll give answers to those questions. And I don't think we'll have, yeah. Aren't the uh, what are Nielsen transformations? In the non-commutative, I am not sure what. Acha, I don't know. I've seen proofs of Nielsen-Schreier without that, so I'm not sure about what the. Uh-huh. Acha. Uh-huh. Acha. Okay. I did not know about that, but nice. It's cool to know. Huh? Yeah, with the thing. Exactly. Yeah. So I don't know if this is what Nielsen. Not in the group. Okay, I'm not sure what those are, but we can look those up later. It's a good reference. Nielsen transforms. We can look that up. Essentially, what a fold does is whatever we would have tried algebraically, we would have tried to simplify this, right? So we would have tried, oh, there's a B inverse here, there's a B at the start. Maybe let me multiply those together and get something. That's exactly what that is doing. Because a B inverse is an edge going out of the vertex. A B at the start is an edge going out of the vertex. We're identifying them together. So we're cancelling that B out. So that's what folding does, and does it much more effectively, right? Good. So we've gotten this delta H. Any questions? out. Okay, fine. So now we have this graph. We are just going to focus on this graph now. Okay, and A going here, A going here, B here, B here. Okay, the rank of H. I am giving the answers to those questions. Okay, the rank of H. So in the delta H, in the unfoldable graph, do this: number of edges minus the number of vertices plus 1. That's the rank of H. So in a graph, so in general, if anyone knows algebra, graphs have fundamental groups as free groups. Okay, so the fundamental group of a graph is a free group, and the number of generators on which this group is free, the rank of that free group is exactly this. You can prove this using some arguments. You have to collapse the maximal tree in a graph, some sort of a homotopy. It leaves the fundamental group invariant, and you can show that this is the number of loops you'll be left with at the end. The rank of H is exactly this, which in this case turns out to be 1, 2, 3, 4. So 4 minus 2 plus 1 is 3. So the group we started out with, which has 4 letters, is in fact free on 3 letters. Okay. What are the generators? What are the letters on which it is free? So to do that, our base point was this, right? Select a maximal tree of this graph. Okay, a maximal tree is just one edge here, right? One edge covers everything, fine. Look at the loops in this graph starting at this vertex which contain this maximal tree. So what sort of loops are there? Well, I could first have some loop like B B inverse A, which is just A, right? I could go here and then I could come back, and that homotopes down to just the A loop. Okay, so I could have A, or I could have B squared, or I could have B A B inverse, right? So these are our 3 generators. We just read them off the graph. See what we did? So H that we started out with is in fact isomorphic to the free group generated by those 3 letters. What are the 3 letters? A, B squared, and B A B inverse. Any questions so far? So first question is answered. We have found out what the generators are already. Maybe a little mysteriously, but we have found them out. Are you asking me why this is true, or are you asking me how I got it? Huh. So you are at this vertex, right? Look at loops made at this vertex. Loops as in edge paths which start and end at the vertex. Okay. So an edge path which does that is B and B back, right? So B squared. So that is one of the generators. Another generator would be B A and then B inverse. Okay. Or even B A B. Those either of them would work. Okay. Or you could just go here, that is A. So these 3 are the generators. Okay. Is some W in H? So can you guys give me a word, like let's say a 4-letter word? Yeah. ABA inverse. Okay. Fine. ABA inverse. I want to check, is ABA inverse in this H or not? Does this belong to H? So what I do is I have this delta H, right? A, A, and then B and B, right? I have this delta H. Just pick a point and attach a loop there. Loop as in what we started out with for H, we made the loop which read off that word, right? So we are making a loop here which reads off this word that we want to check if it's there or not. So it is A, any vertex. It doesn't matter, yeah. Pick a vertex and do it. A, B, A inverse, okay? This is the word. Perform folding on this graph. If it gets back to our original delta H, then this word is in H. If it doesn't, then it's not in H. So this is my favorite application, because this is, you couldn't possibly imagine how to do this even when you know the generators. Okay, maybe this is easy to do with the generators, but given a random word, it's very difficult to see if it's in the group or not. And all you have to do is folding. So here what we can do is we can fold these two together, right? These two A edges, we can fold them together to get just one A edge, sorry. Okay, and then this B makes a loop over there, right? B makes a loop there, and this is an A edge. The A edge can get folded along that again. Okay, so that gives you a B loop over here, right? What else can be done? I can fold this B along this loop, right? So I have effectively folded everything now because I can fold this B along this loop, right? So now I'm getting a B loop, a loop, and a B loop and a A loop, and the two A loops get folded together, two B loops get folded together. So you are essentially what you're going to get is just this graph, whatever this graph is. I mean, yeah, not disproportionate, just the same R2 that we started out with, A and B. Okay, and this is not the same as this delta H that we started with, right? So this word isn't in the group. Yes, exactly. That's what we're trying to. Yes, I guess. Yeah. Attaching the generator as into the uh, tree, not the tree, graph. Hmm. Something like that. Yeah. If we are sorry, can you speak up a little louder? Huh? Huh? I suppose so. Yeah. It's probably going to be the full group. If I fold them down. Sorry. Sorry. Wait. What relation should be in it? Huh? No. I mean, I could replace this BAB by BAB inverse by BAB, and I'll still get the same group. Huh? Huh? If we had attached ABA inverse to what? Uh-huh. This graph. Yeah. Okay. Uh-huh. What is the initial one? The okay. No, see, okay. I don't know exactly what you're saying, but I'm saying that if you attach the extra loop and it gives you back exactly this graph, then and only then this word belongs to that graph. Now what he said is actually correct. I mean, if since it gave you this, if I had added this generator to the list of our generators, I would have gotten F2. Because what I'm effectively doing is what how would I have checked if that was F2 or not? I would have made that huge graph for it. I would have folded. So folding doesn't care about the order, so I could have folded everything relating to this graph first, then I would have had this reduced graph with that extra loop, and then I fold and get this, right? And now what are the generators of this? Just A and B, so it's the full group. Hmm. Shouldn't we add AB inverse to what vertex? This vertex. And not to that one. No, it doesn't matter. Doesn't matter. Yeah, I mean, yeah, it doesn't. You can add it to the root vertex. See, the root vertex was arbitrary, right? No. Probably because it's a normal subgroup and it's vertex transitive. Well, yeah, I mean, up to conjugation it is. So in this case, it's this graph is vertex transitive also, right? So it doesn't matter whether we are at this vertex or that vertex. Sure, you can attach it to that, but okay, I guess we can. So we don't have time to prove everything, but I'll just say, because this is my favorite one, I'll just say this: when you attach this G to that graph, right, you're essentially making the graph for this H comma G, like the subgroup generated by the group H, subgroup H, and the element G. So if after folding that graph gives you back delta H, that means that how do I say this? Yeah, this should have been inside the subgroup generated by which is H itself. Does that make sense? Because okay, how do I? write this down properly. I don't know how exactly to say this, but I attached a loop and it went back in. Right, okay, yeah. After folding, if I get the same thing as delta h, that means all the loops that I could have made out of delta h, all the loops that could have been there, they can still be made after the entire extra loop of this g has been folded. Which means that whatever things I could have made with this, which is the fundamental group, it doesn't really matter what that is the fundamental group of uh, this extra thing that let's just call this delta h dash. Okay, this is the fundamental group of delta h dash. Okay, everything that can be made in delta h dash should also be possible to be made in delta h if this loop after folding gets back into the graph, if it gets devoured by the graph, right? So that means this fundamental group sits inside the fundamental group of h, delta h, sorry. Yeah, and if that happens, then the subgroup generated by h and g sits inside h itself, so g is inside h. And if it doesn't happen, if you get something else, then that means that there was some loop in the delta h dash. When you attached this new loop, you could have formed some loop which could not ever have been made using this graph, because if it could have been, then you see folding is reversible, right? If I folded two edges, I can get them back, I can just open them up and come back, right? So if there was some loop which was here, and I'm sorry, what am I saying? G, yeah, if it doesn't get back to the same graph, then that means there was some edge in here which can't be made here. If it could be made here, I could fold it, like I could fold it upward, unfold it upward, and then get back to some loop here. And this is how you can prove membership. So you can just take any word there and see if it belongs in the group or not. Okay, great. What is the index of the subgroup H? I haven't used that, huh? It's okay. Hmm? Sorry, it may not be finite. In this case, it is. So, okay, I'll tell you one thing. Okay, so you guys don't know what coverings are, so I'll just give you a brief idea. If you have a space X, then a covering space of that space is something that looks locally like that space. So, in case of graphs, a covering space is okay. So, I'm claiming that this graph is a covering space of this wedge of two circles. Okay, what that means is, if I look at every vertex in this graph, it should locally look like that. So what does this graph look like locally? In a neighborhood, it looks like there is an A edge coming in, there is an A edge going out, there is a B edge going out, and there is a B edge coming in, right? And in this graph also, locally, the same thing is true. If you check that, the same thing is true. So this space is called a covering space of that. Now I'm claiming that a subgroup H, so I'm working with F2 only here, sorry, a subgroup H in F2 is finite index if and only if delta h, the unfoldable graph associated with h, is a covering, yeah, of R2. R2 is just that wedge of two circles, right? And the index equals the number of vertices in delta h. So the index of the subgroup here is just 2 because there are two vertices. Okay, and yeah, so why that works is I know I'm old, but I'm just trying to give you an overview here. Why that works is, if you have h, any coset of h, so if I multiply h by some g, h is what? H is realized as the fundamental group of something. Fundamental group contains loops at some point, right? If I concatenate a loop with some g, and let's say g is a path between two things, then I essentially get loops at the next point. Okay, so cosets of the subgroup h correspond to shifting the base point by one or something, like let's see here. Okay, h is what? H is the fundamental group of this graph, right? It is, just believe me, it is the fundamental group of this graph. and what we are doing is H corresponds to, that means H corresponds to tight loops meaning loops up to homotopy at V, okay, and HB. So if I multiply this element B with H, what I'm going to get is, now I was looking at loops here, but after looking at a loop, I'm concatenating it with B. So I'm essentially going here, and now I'm looking at loops here, right? So the set HB corresponds to loops at the point at the second base, at the second point in the thing, right? So what I'm saying is, if this is a covering map, so why does it have to be a covering map? Yeah, if and only if, okay, this is required. So it has to be a covering map because I want to look at loops in R2. I want to look at loops in here. I could form any word here, and I want to lift it up to the covering. I want to see what does this loop look like if I took the inverse of that graph map and saw it in here, okay. So the loop could either come back to a loop at this V, or it could come back to something that starts at V and goes to V dash, right? And what was that? So that means it can either be H, right, which are loops at V, or it can be things that start at V but end at this W, okay, which is HB, right? And what have I said? I've just said that those were all the loops in R2, right, which is just F2. So I've said that all the words in F2, they're either in H or in HB. So H is a subgroup of index 2, right? And then, so that's why if you had a covering ensures that any loop can be lifted up, and as long as the loop can be lifted up, you can say that the number of vertices that are there, I have paths between these vertices, right? So I can just go from one vertex to the next using this path, and those will be the number of cosets, and that's why this is the index of the subgroup. Okay, moving on. The next thing will be, when is a subgroup normal? Okay, and I'm just going to say this result. If this space that you had, delta H, if this is vertex transitive, that means that this graph is invariant under you switching vertices. If I sit at this vertex V, the graph looks the same. If I change the vertex V to the vertex W, the graph looks the same. Or formally, there is an automorphism which takes the vertex V to the vertex W. Then if this holds for all pairs of vertices V and W, then the graph is called vertex transitive. And if the delta H that I get for some subgroup is vertex transitive, then I can say that the subgroup generated by that is normal. That's a small result in algebraic topology. And okay, now here's the last thing I'll do. Sorry for going time, but let's just do this one little thing. Okay, generated non-trivial. I think there were some conditions there. I don't remember that, but okay. So it turns out that, by the way, this H is normal in there because this graph is vertex transitive, right? It's symmetric about the vertices. I don't care if the vertices are switched or not. Now, huh? Anyways, it's index 2 exactly. Yeah. So now here is a result. This is really a corollary. What I'm saying is, a finitely generated non-trivial normal has finite index. This may not generally be true, right? I'm saying that you take a subgroup which is non-trivial and finitely generated. If it's normal, then it has finite index. Okay, this isn't usually true, but now why is it true here? So what you can do is, either, so you draw this petal wala graph for H. Okay, you start folding it, you will get delta H. Okay, if delta H to R2 is a covering, if is a covering, right, yeah, if it is a covering, delta H is a finite graph, right? So this covering must have finite index. I'm given that the subgroup is normal. I'm saying that if I get delta H to R2 as a covering, as in every vertex locally looks like there is a BH coming in, BH going out, AH coming in, AH going out, and that means it's a covering, then it has finite index. Then F2 to H is finite. Okay, else what happens? Else it's not a covering, right? If delta H is not a covering, I can make it into a covering. So how do I do that? The last thing. Yeah, let's look at this subgroup generated by AB. Okay, so for AB, what will I do? I will draw the graph, one petal, right? And there is just I read of A and B, right? This is definitely like this is not foldable, right? So there is an immersion directly to R2. Okay, A and B. There is an immersion like this. This is not foldable, but now the thing is, this is not a covering either, right? Because it doesn't look like there's an edge going in, edge going out, anything. So what you can do is you can attach the edges. Okay, just there wasn't a edge coming in, so I attached an edge. Okay, there wasn't a B edge going out, so I attached edge. And now these vertices are again there, the condition is not fulfilled for them, so I attach more edges. Okay, and I attach more edges, and I keep going and I keep going, and now I've attached trees, like infinite trees on this side, and there are infinite trees on this side, whatever. Okay, so there are trees, and now this huge infinite graph is a covering, because at each point locally you have those conditions satisfied, you have an edge going in, edge coming on, whatever you wanted. Okay, fine. So this is the way you convert some non-covering wala immersion into a covering wala immersion. Okay, by attaching trees on the sides. Okay, so now if it is not a covering, then I can promote it to a covering. But now, since the subgroup was normal, the covering has to be vertex transitive, right? But a vertex transitive covering means now we started out with a graph, right? That graph had loops. This loop was AB, right? So this vertex, there is a loop at this point, but that means I can't take this vertex outside this loop, because if I do, then there is a loop in a tree, but that's not true, right? So this graph is not vertex transitive, else the covering graph, the covering delta h tilde is not transitive, right? And then that's a contradiction. So that means that it had to have been a covering to begin with, and if it was a covering, then it was finite index. So we've proven that all normal subgroups of all finitely generated non-trivial normal subgroups of free groups have finite index. So this all of these things work for Fn just as well as they work for F2. You just need to add the labels more, and then you need to do all of these things. But yes, that was all I wanted to talk about. Thank you for listening. Any questions, by the way?
Yeah.
Huh? References, yes. Uh, so by the way, that means this is not a normal subgroup of then finitely related normal subgroup is finite index. Yeah, if it was a normal subgroup, then it would have had finite index. That, yes, references. Okay, this is an excellent book. Like, you'll get an introduction to all the topics, and it's wonderfully written. It's really nice. So there is a entire chapter in foldings, which is where I took most of it from. Then you can look up this paper, topology of finite graphs, by Stallings. He introduced this technique in that paper, and you can look at, if you are concerned with computations, and why did I take that maximal tree over there to get the generators? How can I get new generators in terms of the old ones and all of that? Then you can look up this particular paper. Stallings is folding and Stallings folding and subgroups of free groups by some author, Kapovich and Masnikov. K and M. Just search it up. You'll get it. Any other questions? Okay, great.
So if there are no other questions, let's thank the speaker once again. Yeah. Thank you so much for attending.
Thank you.